Hello. In this video, we will examine and try to practice on AP mechanics, and basically we're going to try to solve three problems on Newton's laws, conservation of energy, circular motion, and air resistance. Well, let's start with our first example, where we see this setup where we have a motion detector, an object that has a mass of 0.8 kgs, a pulley, another object that has a mass of 0.3 kgs, and another motion detector. Now, if we read the question, they mention that students design an experiment in order to investigate friction. So probably the block 1 will be on a surface with some kind of coefficient of friction. Block 1 has an initial mass of 0.8 and it's on a rough surface, and block 2 has an initial mass of 0.3. And we need to figure out what should be the minimum value of the coefficient of static friction to keep the system at rest. So we have a system of two objects, and it would be nice to start with a free body diagram. So we have the force of gravity on the second object. The force of gravity, it is mass times g. So we've got the value 0.3 times 9.8, or 0.3 times 10 for simplicity. This will be 3 Newton, and a tension that at the moment we don't know. Another tension, the same tension on the other side of the rope. Force of gravity on block 1, so force of gravity is 8 Newton, and normal force that it is equal to the force of gravity, 8 Newton, and the friction, since the object is at rest, this is static friction. Now we can work for the system, or we can work for each object separately. If we work for the system, we can say that the F net on the system is 0, since both objects are at rest, and the external forces are only applied on the system. The external forces are the friction and this force of gravity. The normal force and this force of gravity cancel each other, and the force of tension is an internal force. So force of gravity on the second object minus force of friction is equal to 0. So 3 Newton will be equal to the force of static friction. This is equal to mu static multiplied by the normal force. So the mu static will be equal 3 over 8, or approximately 0.38. And the coefficient of friction doesn't have a unit. For part B, the coefficient of friction is such that the object is released from rest, and the other object is starting to travel across the surface. So basically both objects will start traveling with the acceleration is equal to 2. And we need to figure out what is the coefficient of kinetic friction. Now we have something similar here. It's just that the force of friction changes. It's just that the friction now becomes kinetic friction, and we need to figure out what is the coefficient of kinetic friction. So we need to find the mu k. But again, we have a system of two objects that is accelerating. So we will start with F net for the system is equal m total, which is m1 plus m2, multiplied by the acceleration of the system. Again, the only forces that are applied the only forces that we will consider are the external forces, so we don't care about the tension. The normal force and the force of gravity are external forces, but they cancel each other. So again, we have 3 Newton, that it is the force of gravity, minus the kinetic friction. So 3 Newton minus the kinetic friction is equal to m1 plus m2, so 0.3 plus 0.8, if I'm not mistaken, okay, multiplied by the acceleration that it is 2. Now, we don't need to find the friction, we need to find the coefficient of friction, so we have to replace wherever we see fk mu multiplied by f normal. It is equal to 1.1 times 2, so 3 minus mu multiplied by 8 Newton, that it is the normal force, it is equal to 2.2. We separate the terms of this equation, so 3 minus 2.2 is equal mu times 8. This is 0.8 is equal mu times 8, and from this we bring that the mu kinetic is equal to 0.8 over 8, or 0.1. And we can continue to another question after this. Again, what we did so far, basically it is try to find the coefficient of friction for a system, for a surface, the coefficient of static friction, where we consider that the object is the system is at rest, and we apply Newton's first law for the system, so F net is equal 0. And later, when there is acceleration, we do the same task for F net is equal m times a, but again for the system. We continue to the second question for today, which is an application of probably circular motion from what we see, maybe Newton's laws, and since the object is released from a height and it will move downwards, and then maybe it will perform one complete rotation on this track, so maybe we will also use the law of conservation of energy, the law of conservation of mechanical energy, since as the object is released, its potential energy is converted to kinetic energy and the object starts moving. So we have a block of 3 kgs released from rest at point A and travels in a surface with negligible friction through a surface, the loop, okay. Now point C is the highest point of the loop and point B is the point that it is furthest on the right, and we need on the dot below to draw and label the forces acting on the block, so just we need a free body diagram. So the object is coming to the bottom of the track and then it starts moving upwards and it reaches point B. Now at that point, for sure there will be a force of gravity, so we need an arrow to represent this force of gravity, and since the object is moving on a horizontal, it is moving on a circular track, for sure there will be a force that points towards the center of the circle. This is the centripetal force. However, the nature of the centripetal force in this case is the force from the surface of the track, so actually it is a normal force. So these are the two forces that are applied on the mass as it reaches point B. Now, we know that the height is 1.5 meters and the radius of the track is 0.5 meters, and we need to find the speed at block B. Now, I think it mentions that there is negligible friction, so we can apply the law of conservation of mechanical energy. So since there is no friction, we can say that the mechanical energy at point A and the mechanical energy at point B, they will be equal. Mechanical energy at point A means kinetic energy at A plus potential energy at A is equal to kinetic energy at B plus potential energy at B. The object is released from rest at point A, so the kinetic energy at point A is 0, and the potential energy is mass times g times height. Since we need to find the speed, we will substitute the kinetic energy with 1 over 2 mass times velocity at p to the power of 2, plus the potential energy at point B. Now we have to be a little bit careful. At point B, the height is equal to the radius of the track, so the potential energy, it is mass times g times height, or mass times g times the radius of the track. Now on this equation, the m can be cancelled, and what we have is, let's consider 9.8 the value of g, 9.8 times the height, that it is given 1.5. It is equal half velocity b to the power of 2 plus 9.8 times the radius, that it is 0.5. And we need to solve this equation for VB. So first we'll take this term to the left, so 9.8 is the common factor times 1.5 minus 0.5, so just 9.8. It is equal half VB squared, and if we multiply by 2, 19.6 is equal VB squared, so the velocity B is root of 19.6. This is approximately 4.4 meters per second. And this is the speed at point B. Obviously the speed is upward, so we can consider it positive. We can continue to part B2, where we need to calculate the value of the net force at that point B. Now, we know that at point B there are two forces, one force of gravity and the centripetal force. In reality, this is the normal force, but we can say that it is F centripetal because it points towards the center of the circle. Now, the force of gravity, it is mass times g, so it is, I think we know the value of the mass, 3. So 3 times 9.8, this is 29.4 Newton. And the normal force, which is F centripetal, it is mass times v squared over the radius of the circle. So it is 3 times 4.4 to the power of 2 divided by the radius, that it is 0.5. So if I'm not mistaken, from this we will find approximately 118 Newton. And we see that the angle between these two forces is 90 degrees. So the net force will have a direction towards the diagonal of this parallelogram. So this is the net force. And in order to find the net force, we will apply the Pythagoras theorem. So it is F centripetal to the power of 2, or 118 to the power of 2, plus the force of gravity, which is 29.4 to the power of 2. And from this, we will bring the result of approximately 119 Newton, which is our final answer. So again, an application of actually not Newton's laws, an application of law of conservation of energy for a track that has no friction, with the free body diagram and finding the net force on a certain point of the track. This point can be either point B or point C. In the case of point B, we have two forces that are acting perpendicular to each other. If it was at point C, we would have to calculate force of gravity and normal force in the same way. But the net force would be the sum of the force of gravity and the normal force. And we can continue to the last application for today, which is, if I'm not mistaken, a problem regarding air resistance. So we have a mass that it is subject to a resistive force, that it is proportional to the velocity v. So the value of the resistive force is minus 15 times the velocity. And the question is, does the magnitude of the net force increase, decrease, or stays the same as the ball moves upward? Now, as the ball moves upward, so there is a velocity upwards, and there is a force of gravity, and there is a resistive force opposite to the motion, so the resistive force Fr, that it is subject to the speed. So the object is thrown vertically upward. Now, as it moves upward, the force of gravity remains constant. However, the resistive force, it is proportional to the speed. So the value of the resistive force is 15 times the velocity. But as the object is moving downwards, the velocity decreases, so the value of the resistive force decreases. And we have two forces, one remains constant, the other one decreases. So the net force is decreasing. And the reason why it is decreasing is we say that as the mass moves up, F net is equal, the value of F net is equal force over resistance plus force of gravity. We say that the force of gravity remains constant, but the F over resistance is proportional to the speed, and the speed decreases. So it makes sense that the sum of these two values will also be decreasing. And we need to draw a free body diagram for this motion. We'll draw exactly the same like what we draw here, but in a little bit better way. So here is the ball, and there are two forces. One is the force of gravity, and the other is the air resistance. Again, the object is moving upward. Now, on the free body diagram, we don't draw the velocities, but the reason why the air resistance is downward is because the object is moving upward, so the velocity is upward. But again, in the free body diagram, we don't need to draw the velocities. And finally, we need to write and not solve a differential equation for the speed as the object is moving upward. Now, in order to do that, we will start with Newton's second law. So F net is equal mass times acceleration. Now, the F net is the sum of these two forces, so force of gravity plus air resistance. However, since these forces of gravity, since these two forces are acting downwards, we can consider that they have a negative direction. This is equal to mass times the acceleration, that it is dv over dt, so it is the first derivative of velocity, and the force of gravity, it is mass times g, the air resistance, it is 15 times r, actually I think it is 15 times v, let me just check, yes, 15 times v, and this is equal mass times dv over dt. This is a differential equation that has the derivative of the velocity. Now, although the question clearly says do not solve this question, we can at least show that we have a clue about how to solve this, which is basically we will need to try to separate the variables. And here we have two variables, the velocity that appears on the left side of the equation, and at the right side of the equation on the differential, and the time. So what we can do is multiply everything by dt. So the dt now appears on the left side and the dv appears on the right side, and I can divide over mass both sides, so we have dt over dm, and I can also, dt over m, and I can also divide this equation with this bracket, so we'll have dt over dm is equal minus dv over mg plus 15v. So by doing this, we have the time on one side and the velocity on the other side. But again, this is not 100% necessary, since the question says do not solve this equation. And finally, we need to calculate the terminal velocity as the object moves downwards. So as the object moves downwards, we have the force of gravity, that it is mass times g, and since the velocity is downwards, the air resistance will be on the opposite direction, so it is 15 times v. Now, at the terminal velocity, the net force is equal 0, and this means that 15 times v, it is equal to mass times g, so 15 times the speed is equal to the mass, that it is 0.2, multiplied by the acceleration of gravity, which is 9.8, so 15v, it is equal 1.96, and dividing by 1.5, we find, divided by 15, we find that the terminal speed is approximately 0.13 meter per second. So that's it for today. Thank you for watching.